So this handsome fellow with this dashing wig is Robert Boyle, an English chemist and one of the founding members of the Royal Society in England, the first real scientific society. One of the areas he investigated, because back then everyone investigated everything, was gases and changes in gases. And specifically, he investigated the relationship between the pressure that you apply to a gas and the volume of that fixed quantity of gas, the same number of particles of gas. He used a piston, a movable piston. And what he discovered, and this shouldn't surprise anybody who's been paying attention for their lives, was that as you increase the pressure, the volume decreases. Okay, you push on that piston, the volume inside that container is going to decrease. And he collected a lot of data, he graphed it, and you get the graph you see there. And that's your classic inverse graph, y equals 1 over x, or some constant m over x. So it's an inverse relationship. And the way he said it was that the volume of a fixed quantity of gas maintained at constant temperature is inversely proportional to the pressure, blah, blah, blah. As an equation, V equals some constant times 1 over P, the inverse of the pressure. If we solve for the constant, multiply both sides by pressure, we get PV equals some constant. Around the same time in France, Jacques Charles, and that's how he would have pronounced his own name, you can call him Charles, that's fine, was investigating temperature-volume relationships of gases. And what he discovered was that, and again, this doesn't surprise anybody, temperature and volume are directly related to each other. As you increase the temperature, the volume increases. You've seen this. You buy one of those helium-filled foil balloons at Ingles. In the winter, you take it outside, it starts to shrink and gets all sad and wrinkly looking. But as soon as you take it inside a warm house, it pops right back up to being full. You know, the gas fills the balloon to straining, it looks full, looks happy, it's a full balloon again. As you increase the temperature, the volume increases. As you decrease the temperature, the volume decreases. And he graphed it, and we get the straight line that looks like y equals mx, which he said is volume is equal to some constant times temperature. We solve for the constant, like we did with Boyle's law, and we get V over T equals some constant. Now make sure you know whose law was what. Boyle was pressure and volume, Charles was volume and temperature. You're going to need to know whose law was which factors. Make sure you get that memorized. The best bet is to come up with some mnemonic, some sentence. So, PVB, pressure, volume, Boyle. VTC, volume, temperature, Charles. Come up with your own sentences to try to remember those things. The more outlandish or gross, the better you remember them. The third one that we need to look at is Avogadro's law. And this is actually his law. Avogadro's number was not discovered by Avogadro. But because they used Avogadro's law to figure out the number of particles in a mole, they named that number after him. He really had nothing directly to do with it. But here's the law they based that on. Avogadro's law says that equal volumes of gases at the same pressure and temperature have equal numbers of molecules. We would now say today equal volumes contain equal moles at the same conditions. In other words, volume is some constant times and the number of moles. So if you have a mole of argon gas, a mole of oxygen gas, and a mole of nitrogen gas, they will all occupy the exact same volume at the same temperature and pressure. They'll have different weights, because whereas one mole of argon weighs about 40 grams, and a mole of oxygen is about 32, and a mole of nitrogen is about 28 grams. But they occupy the same volume, and that's what's important. Avogadro also had what he called the law of combining volumes. He said that when you do a reaction of gases, if all the reactants are gases and all the products are gases, that the volumes of reactants and products end up being in a small whole number ratio. So hydrogen and oxygen to make water ends up being in a 2 to 1 to 2 ratio. It's exactly the same ratio as the molar ratio. And that's what led to Avogadro's law. Okay, the ratio of the moles is the same as the ratio of the volumes if they're gases at the same temperature and pressure. Very, very useful for doing stoichiometry, which, hint, hint, we will be doing. So we can do some qualitative looks here. We don't have to do math for these every time. But if you have, in that container in the picture, some set quantity of gas, the top thing can move up and down. We can adjust the volume, we can adjust the pressure, and it's got a little spigot to the side where we can adjust the the number of molecules in there. So if we heat the gas while keeping the piston in the same place, so the volume does not change, and we heat up the gas, how does that change the distance between the molecules? Well, heating the gas, the temperature change, means the particles are moving faster overall. The average kinetic energy or speed increases. But does the distance between the molecules change? And the answer is no. It's the same number of particles in the same volume, they're just moving around faster. So the average space between them doesn't change. However, the pressure would change. As you heat it, the pressure increases. Because, remember what pressure is. Pressure is the force of the particles hitting the wall of the container. If they're moving faster, that means they're hitting the walls of the container harder, which means it's a greater force. If the force is greater, the pressure is greater. The number of moles of gas in the container, not changed. It's the same number of particles, nothing went in and out. Okay? For part B, if we reduce the volume of the container from 1 liter to half a liter, so we squeeze it down, how does that change the distance between the molecules? Well, if we're giving them less space to move around in, we're going to cut down the average space between them. Right? They're going to be closer together because we're packing them in. We're squeezing down, reducing the volume. The pressure of the gas is then going to increase because they'll be hitting the walls of the container more frequently. They have less space or less distance to travel to hit the next time. So it's going to be hitting more frequently. So the pressure would go up because we have more collisions. So that means more pressure, more force and more pressure. Number of moles, not affected because nothing went in and out of the container. It's still a closed system. For part C, if we leave everything else the same and we put more moles in there, well, more moles of gas and additional gas particles through that little valve there, the distance between the molecules is going to decrease because we're crowding more in there. It's like if you had 3 people in an elevator and you put 5 more people in there, the average space between the people decreases because you're packing more in. The pressure of the gas similarly will increase. You have more molecules, so be hitting the walls of the container more frequently. That means higher pressure. And the number of moles of gas, well, we just put more gas in, so the number of moles went up. We can also think about what happens to the density of a gas. And we're going to use the same three instances here to talk about the density. Remind yourself of what the equation for density is. Density is mass divided by volume. So the density of the gas only depends on those two things, the mass of the particles in there and the volume they contain. Anything that doesn't change the mass or the volume doesn't change the density. So for part A, if we heat that up, the particles are moving faster, the pressure increases, but that has nothing to do with the mass. It's the same number of particles, so the mass has not changed. The volume has not changed. Part A even tells us constant volume container. If the mass hasn't changed and the volume hasn't changed, the density hasn't changed. For part B, if we compress it, we're reducing the volume. Same number of moles, same grams, in a smaller volume. So if we think about the equation, mass over volume, if we make the denominator smaller, that means the density is getting bigger. Think of 3/4 versus 3/2. The smaller denominator is actually a bigger value. So if we compress it, we're actually increasing the density. For part C, if we add more gas, we're increasing the mass. We're adding more particles, more mass in the particles. The volume hasn't changed. But if the numerator goes up, then the density overall will go up. Think about 3/4 versus 5/4. The bigger the numerator, the more mass, the bigger the density.